last week, we did a titration, and that involved taking a weak acid, which was acetic acid, and calculating the concentration of it by adding a strong base to it, which was sodium hydroxide. And we kept adding sodium hydroxide until there's a dramatic pH change, which happens around the point where the two concentration of the acid and the concentration of the base are the same. And at that point, we get a big change in pH because we go from having no free sodium hydroxide to now having free sodium hydroxide, and the concentration of sodium hydroxide will increase the pH substantially. So this is a sort of similar situation, but slightly different in that now, instead of just adding sodium hydroxide to acetic acid, we're going to make a solution of acetic acid and its conjugate base. And what's the conjugate base of acetic acid?
Sodium acetate.
Acetate ion, that's right, acetate ion. And so we'll find out what happens when we have both acetate ion in a fairly high concentration and acetic acid in a fairly high concentration. We make what's called a buffer. Anyone tell me what a buffer does? What does a buffer do for us?
It resisted a drastic change in pH.
Exactly right. Excellent. If we add sodium hydroxide to just water, the pH will rocket up very, very quickly. But if we have a weak acid and a conjugate base in there, if we add either acid or base, the pH doesn't really change that much. It'll change a little bit, but it really won't change that much. And so we're going to learn why that is and how to make a buffered solution. So we're going to look at what the characteristics of buffered solutions are. I think I talked a little bit before about how your blood is a buffered solution that uses CO2 dissolved in water to make carbonic acid. And so the weak acid in your blood is carbonic acid, and the conjugate base is carbonate ion. And so having both of those present at the same time means that we pretty much keep the same pH in our blood at all times. And any sudden change in either base or acid concentration is basically wiped out by having buffers there. So we're going to learn how to calculate, how to make buffers, learn about what is the relationship between the pKa of a weak acid and the approximate pH that it can buffer. Because we'll learn that basically you want to have a buffer system where the pKa is pretty much near the pH you want to make. For instance, the pKa of, anyone know what the pKa of acetic acid is? Roughly.
Is it 4.75? Or?
That's right, man. Crushing it tonight. That's Eva, right?
Yeah.
There you go. Yeah, it's around 4.75. So that means that the pH, it's really good. A pH, a buffer system made out of sodium acetate and acetic acid would be pretty good at maintaining a pH of around 4 or 5. If you wanted to have a pH around 8, however, that would not be the buffer system you would want. You would want something else. With it, you probably wanted a weak base with a pKb of around 8. So we're going to prepare buffered solutions. We're going to first figure out how much sodium acetate we should use to make a sodium acetate solution. we're provided with a 0.1 molar acetic acid solution, which is nice because we could have just actually diluted it from the vinegar we used last week. But I don't think we have to do that. So, as Eva mentioned, a buffer is a solution that resists big changes in pH. Now, if we add acid or base, it resists changes to pH. Now, if we just used the weak acid, it would resist changes to pH if we added a strong base. But if we added a strong acid, it really wouldn't do anything. The pH would go down. That's why we want to have both the weak acid and the conjugate base there. So so HA is considered the weak acid, which doesn't dissociate very much. H plus and A minus, this being the conjugate base that's produced. So remember that this reaction goes in both directions, and especially goes backwards because it's a weak acid. So we don't make very much H plus, and so the pH doesn't go down tremendously. So what happens when we add a strong acid to the system? We increase the concentration of H plus, and we push that reaction back towards reactants, reactant being the weak acid. So basically what we've done is if we've swapped a strong acid, which is H plus, and we've swapped it for a weak acid, which is HA. And so the pH doesn't change very much. Now, what happens if we add a strong base? Well, if we add a strong base will react with the acetic acid and reduce the concentration of acetic acid. It actually will react with the H plus that's already there and make water. So it will reduce the concentration of H plus. And we haven't really learned much about equilibrium. This is something important to learn. If we change something in the equilibrium will reestablish itself to try and bring things back into balance. So what will happen when hydroxide ion interacts with H plus and makes water? Well, we have then lowered the concentration of H plus. What will happen to the equilibrium? Well, what happens to the equilibrium is that it tries to reestablish that amount of H plus by pushing the reaction forward. So it pushes the reaction in the direction of making more product. So it dissociates more acetic acid and produces more H plus and more acetate. So no matter what you add, the equilibrium of having the weak acid of the conjugate base will push the reaction in one direction or the other direction. And what it does, as I mentioned here, it takes a strong acid and converts it into a weak one, HA. The OH minus, which is a strong base, gets converted into acetate ion, which is a weak base. And so basically that's what a buffer does. It takes a strong acid, turns it into a weak one. It takes a strong base, turns it into a weak one. And so that's why the pH doesn't change as dramatically, because we're switching strong and weak. So the pH doesn't change much. However, this won't work if the concentration of our acetate ion and acetic acid is overwhelmed by too much H plus or too much OH minus. And that has something to do with buffer capacity. And that's sort of the part 2 of the lab tonight. The first part, we'll be looking at how a buffer system works in maintaining the pH. And in the second part, we'll dilute our buffer and see that after a certain point, it loses the capacity. Oh dear, don't do this again. Come on. Everyone still with me?
Yes.
Okay, that is a pain. So once we've overwhelmed the capacity of the buffer, once the concentration of either H plus or OH minus is greater than the concentration of the buffer, then the pH will change dramatically. And that makes sense. I mean, there's only so much acetic acid or acetate ion present to sort of do that conversion of changing a strong acid to a weak one or a strong base to a weak one. There's only so many ions present. And once we overwhelm that, basically you've overwhelmed the capacity of our buffer. So this should be sort of an old friend here, because this is the good old Henderson-Hasselbalch equation again. And so remember that with a weak acid, the pH is equal to the pKa of the weak acid. And remember, pKa just means minus log base 10 Ka. And the Ka is the equilibrium constant, which tells us concentration of the products of the dissociation, which is H plus and acetate, divided by the reactant, which is the acetic acid at the beginning. So Ka is low for a weak acid because it doesn't make very much H plus an acetate ion. It dissociates very little. So if we wanted to figure out what the pH is, we do that by this equation here. We figure out what is the concentration of our acetate ion, and what's the concentration of the undissociated acid, and we take the log of it. Add that to the pKa, and we get the pH. So this sort of shows you basically why it is that buffers only really work very well near their pKa. Because if we have to change this ratio by any more than about, say, 10 to 1 or so, then we run out of buffering capacity pretty quickly. If I have to have 1,000 times more acetic acid than acetate ion on top, well, then that's terribly little acetate ion. And so it's really not going to be able to buffer the system very well. We'll get the pH we want, but the minute we add a strong base, it'll just overwhelm it because my concentration is so super low. So that's why we're going to be using tonight, we're going to be making buffers of pH 4.7, which is pretty much where the pKa is. So that's right in the sweet spot of where this buffer system should work. And then we're going to go 1 log unit above and 1 log unit below. So we're also going to make a buffer at pH 3.7 and pH 5.7. And we'll be able to do that just by altering the ratio of acetate on top and acetic acid on the bottom. And I think they give you an example how to do that. So let's look at how we would actually do that kind of calculation. This is called an ICE table for initial, change, and then equilibrium. So what that means is at the beginning of, if I had a solution of 33 millimolar acetic acid and 56 millimolar acetate ion, what would the pH be? And we can figure that out by looking to see what happens in this, what is the change that will occur. So the change that will occur is some of the acetic acid will dissociate, and we'll call that X. We don't know how much of it will dissociate. We'll figure that out. So some of it will change, some of it will dissociate. And so the concentration of acetic acid will go down by minus X. H plus will increase by exactly the same amount because it's a 1-to-1-to-1 ratio. For every mole of acetic acid that dissociates, you get a mole of H plus and you get a mole of acetate ion. So H plus will go up by X and acetate will go up by X as well. So then at equilibrium, our concentrations will be the initial concentration minus X for acetate. The concentration of H plus will be X, and the concentration of acetate will be 56 millimolar plus X. Then we solve for X using the pKa of acetic acid. So the pKa of acetic acid is 4.75. Therefore, the Ka is 10 to the minus 4.75. And what is the Ka? The Ka is the two products, which are H plus and acetate. So O56 plus X, which you really can't see at all here. And we divide that by 0.033 minus X. And then we just solve for X. And by getting the concentration, that gives us the concentration of H plus. And when we know what the concentration of H plus is, we can figure out what the pH is. So I'll go over this probably more. I'll actually probably make a video about this as well, because there's a lot going on here. And really, there's really only one question, I think, in the report that you need to answer about this. So I'll deal with it a little bit later, because tonight we got to actually do the experiment. But this is how you would do that kind of calculation. I'll go into more detail a little later. So this just basically gives you the same sort of information of, if you're going to make a buffer, you have to decide which acid conjugate base you're going to use. And it makes the point I've just made, that you want to have approximately equal concentrations of both A minus and HA, because you want to be able to absorb both acid and base. So you want to have approximately equal concentrations. Well, when you have approximately equal concentrations of conjugate base in the acid, the pH of that is going to be the pKa. And that explains why you want to choose a weak acid with a pKa at approximately the pH you want to balance, that you want to buffer for. If you want to buffer for pH 6, you want to have a weak acid that has a pKa of around 6, and same with bases. So what are we going to make? So these are all the stuff we're going to be making tonight. So the acetic acid is already diluted for you, so we don't need to dilute that, although that would have been fairly straightforward. We have 10 grams of sodium acetate, so that's our conjugate base. This is a different pH indicator than we used last week. Last week's pH indicator really only showed you the difference between lower than pH 8.5 and above pH 8.5. That was the phenol phthaliin. So that changed color above pH 8.5. This particular solution has a whole series of different indicators in it. And so it's basically a different color for every pH from about 4 to about 9. I think for 3 to 9 is the basic range. So it'll be a slightly different color for each one. So it's perfect for what we want to do tonight, since we don't have a pH meter. This is the chart that will tell you what the pHs are. And you can see that it's sort of lighter colored at low pH and then darker colored at high pH. We're going to be doing our experiment in a 24 well plate, and we're going to be using it twice. So we're going to be washing it midway through and then doing a second experiment. So we're going to need the hydrochloric acid. They expect you to have the 1 molar NaOH, which will dilute, and the 1 molar HCl. Like I said, there is, from one of the other experiments, a bottle already made of 0.1 molar HCl and 0.1 molar sodium hydroxide. So if you just want to use that, I won't tell anybody. So we'll need our balance, because we need to measure the mass of sodium acetate. We're going to be using a whole ton of plastic cups, and get yourself a marker or a wax pen or something you can mark on these, because if you don't, it's going to be a nightmare keeping them all straight. Small plastic cups, a weigh boat, and we're going to be using a ton of pipettes. And you can label the pipettes as well, because you don't want to mix them. If you're using a pipette to draw out acid, you don't want to immediately then put it into base, because that will screw up your concentrations. So where do we begin? Yeah, read through everything completely. Yeah, that would have been nice. So these are the 8 different plastic cups that you will label. Water, 0.1 molar acetic acid. You're going to make 0.1 molar sodium acetate yourself. So hopefully you have already calculated how much sodium acetate you will need to make 50 mils of a 0.10 molar acetate solution using this molar mass. Hopefully everyone knows how to do that. We have our 0.1 molar sodium hydroxide and 0.1 molar HCl. And then we're going to make the 3 different buffers, 3.7, 4.7, and 5.7. So how we're going to do that? Well, we're going to do that by mixing the acetic acid solution and the acetate solution, the sodium acetate solution. And so you pour them in different ratios, and using this equation, figure out what the ratio you need for acetate divided by acetic acid. So they take you through the first one, and it really should help you figure out what the next 2 are. So for 3.7, we need to solve this equation. And so, and at 4.7 and 5.7 as well. But at 3.7, the log of acetate over acid has to be -1. What does that mean? Well, that means so 10 to the -1 power is equal to 0.10. So the ratio of base, or the ratio of the conjugate base, which is acetate, to acetic acid is 10 to 1. That means we need to have 10 times as much acid as acetate. So that means we need to have 9.1 mils of acetate, or sorry, acetic acid, and 0.9 mils of acetate ion. That's 10 times, one is 10 times more than the other. Now, if this is 4.7, that means the log of acetate over acetic acid will be 0. What's 10 to the 0? Anyone know what 10 to the 0 is? 1. 1, exactly. So that means the ratio of acetate to acetic acid needs to be 1. So in other words, they have to have the same concentration. So if we're making 10 mils, that would just be 5 mils of one and 5 mils of the other, because they're equal concentrations. Now, if it's 5.7, that means log of acetate over acetic acid needs to be +1. What's 10 to the 1? 10. 10. That means 10. So that means the ratio of acetate divided by acetic acid has to be 10, meaning now we need 10 times more acetate than acetic acid. So if you're making, again, so if you're making 10 mils of this stuff, that means you need 10 times more acetate than acetic acid. Basically the opposite of the very first one we made at 3.7. At 3.7, you need 10 times more acid. At 4.7, you need equal amounts. And at 5.7, you need 10 times more base, which makes sense, right? Because the more acid you have, the lower the pH. The more base you have, the higher the pH. So that's, if you were paying attention, that's how, you don't even need to do the calculations now. You can just go ahead and make your solutions. So we're going to make 50. Oh, go ahead.
Sorry, can you go back to the previous one?
Sure.
I'm just confused on how we got the 9.1 ml based on the.
Oh, because you
0.9
need 10 times, oops. You need 10 times more for making the pH 3.7 buffer. You need 10 times more acid than base. So the ratio of acetate to, the ratio of acetic acid to acetate needs to be 10. We're making 10 mils. So to make 10 mils of something where you have 10 times more of one than the other means you need 0.9 mils of one and 9.1 mils of the other. So this one is 10 times more than the other one. That's where we get that from.
Gotcha. Thank
Yeah.
you.
So if we were making 100 mils, it'd be 91 mils of one and 9 mils of the other, but we're only making 10. Okay.
Okay.
And you know, if it's 9 to 1, that's probably fine, because it's going to be really hard for us to measure 0.9 mils, believe me. So if you get 9 to 1, that'll work just fine. So we're going to make 50 mils of 0.1 molar sodium acetate. So figure out how much you're going to need and then add it to about 45 mils of water and just stir it until it dissolves. Pour it back into the graduated cylinder and add water to get to 50. That ensures that you've got the right volume, and then rinse the graduated cylinder. So put about 100 in the cup that's labeled water. And then again, 50 mils of the acetic acid solution to the cup that you've labeled already with acetic acid. Add 10 drops of the indicator to the acetate and the acetic acid solutions. Add 20 drops of the indicator to the water. So since the water, you have twice as much, you have 100 mils, add twice as much. So if you haven't got the small bottles of sodium hydroxide and HCl, you can just dilute them from the more concentrated version and just put that in like one of the small cups. Add 2 drops of indicator to each of those. So you want 10 mils. So we're going to be squeezing like 10 mils out of these if you have them. I don't know what the total volume is. Ooh, 15. Yikes. Yikes. So yeah, so we may have to make some new solutions for our next lab. And then make 10 mils of the 3.7, 4.7, and 5.7 pH buffer that we just talked about. So we're going to have cups all over the place. So it's going to be really important to label those and keep them straight, because it's going to be a nightmare of organization. So what do we do with all these solutions? So we're going to get our 24. Here's our 24 well plate. And we use these a lot in science. We use 24 well plates. We use 96 well plates. We use 384 well plates. And I know some places that use 1,536 well plates, generally with robots. I use robots for my 96 well plates because it's much easier having them do all this pipetting and everything than doing it ourselves. But we don't have robots, so we're going to do it ourselves. So put 1 drop of indicator in each well, each of the 24. And then we're going to have it with its 6 sides on 6 wells on each side and 4 wells on the top. So we'll have it, sort of standing up. And then we're going to use our transfer pipettes. And if you look at the transfer pipette, they do have a measure on them just below the bulb that says 1 mil. So basically you want to draw up 1 mil. And again, if it's a little bit more, a little bit less, fine. But you want to get it as close to 1 mil as possible. Add 1 mil of the acetic acid solution to the top 4. And then do the same thing, water in the second 4, sodium acetate in the next one, 3.7, 4.7, 5.7. Then we're going to take a picture, and I got to go get my camera. Take a picture of it, and that will be one of the 4 pictures you'll be taking in this particular lab, because we want to know what the pH is in all of these different conditions. What's the pH of the water? What's the pH of the acetic acid, the acetate, the different buffers? We pretty much know what the pH of the buffers are going to be. Hopefully they'll be close to 3.5, 4.5, and 5.5. Then we're going to actually test. So you should write down, make a note of the pH in each one of these. Match it to the color palette, and make your best guess as to what the pH is. Then, in the second well of the row, we're going to use the pipettes. So let me clear this. So then in the second well, we're going to be adding 1 drop of the HCl solution to each one and sort of swirl the plate to mix them. In the third well, 1 drop of sodium hydroxide. Okay. And then in the fourth well, 10 drops of sodium hydroxide. So we're going to compare adding a little bit of base and seeing if that changes the pH much, and then adding a lot more base and see if that changes the pH much. Then take another picture and make a note of the pH of each one of these plates. Now, what we should see is that a little bit of HCl or strong acid or a little bit of strong base shouldn't really change the color of these. But adding a lot of base might. So we need to make a note and take a picture and see if that occurs. We should see dramatic differences with the water because the water doesn't have any capacity to buffer. So the water should just be changing pH all over the place. The HCl should really, really reduce it. The NaOH should really, really increase it. Now, the second part of the experiment, so we wash this clean, dump it out, rinse it with water, and then dry it in some paper towels, trying to get most of the water out. And then we're going to turn it on its side. So now it's the long way. And we're going to then dilute our buffer. So we're going to make, oops, let me go back. We're going to make 20 mils of pH 4.7 buffer by doubling the volumes we did before. And since it's 4.7, I think we know what those volumes are going to be. Instead of 5 plus 5, we're going to do 10 plus 10 mils, acetate and acetic acid. Add 2 mils of this solution into the first row. So each one gets 2 mils. Then we're going to take 5 mils of this solution and dilute it 4 times by adding 15 mils of water. So that'll be our first dilution. And then add 2 mils of a 1 to 4 dilution. And then we're going to dilute it again. And then we're going to dilute it again. So basically what we're doing is we're lowering the buffering capacity each time. Each time we dilute it, we're reducing the capacity. And the capacity being how much strong acid or base can it absorb before the pH changes. So the second row is a 4-to-1 dilution. And then we're going to take 5 mils of the second dilution and dilute it by 4 times again. That'll be a 1 to 16 dilution. And then all the wells in the fourth row will get the most dilute. Take a color of that. We'll probably want to add a drop of indicator to each well so we can see the pH a little bit better. And then to the second well in each row, let me go back. We'll add, again, 1 drop of the strong base, 2 drops of a strong base to the third well, 3 drops in the fourth, 4 drops in the fifth, 5 drops in the sixth, so on and so on. And then swirl them till we get a color that's no longer changing, and then take another picture. All right, lot to do. So any questions before we get started? Oh, this is what you should see for your color chart. You can see that it's going to work from about pH 4 so to pH 10. And then these are the data tables you're going to be filling out. So when it asks you for initial color, just basically give the pH that corresponds to that color. Okay, so there should be numbers in here. Like, pH, you just put, whatever the color is, pH 4, pH 6, pH 8, whatever it is, rather than trying to describe what the color is. Just do the interpretation and figure out what the pH is. Okay. So any questions before we get started? I'll give you, a good at least 5 minutes to get everything together, and then we'll get started. Any questions before we do that? Hope you have lots of cups. I got my cups labeled.
For swirling, Professor,
go ahead.
do we just do we use something to swirl it, or just use the plate and just stir, like just
swirl.
okay.
Yeah, just gently.
Okay.
And it comes with a top. So if
Yeah,
you're worried about contamination, just put the top on it and then swirl it. And then you can take the top off to get a better picture.
Gotcha.
I'm still doing this rather than, that's what a picture is these days. Okay. I'll see you in at 8:05. We'll get started. All right, let's see everybody here. Ava. I get all my stuff here. So I think the first thing I'm going to do is make my sodium acetate. Let's see, my sodium acetate solution. So hopefully everyone has already determined how much they're going to need. Okay, sodium acetate. That's interesting. See, the sodium acetate crystals are all different sizes. There we go. So notice this says anhydrous on it. Anyone tell me what that means? If something's anhydrous, then what is it?
It doesn't have any water.
That's right. Excellent. Yeah, because as we've seen, some ionic compounds still have water in them, even when they're a crystal, even when they're a solid. That's actually an experiment. I don't know if we might be able to do that experiment to determine how much water is present in different crystals. Yeah, so then not quite 50 mils, a little bit less. Appears to be a little bit of an endothermic reaction. If you feel the cup, it's a little cold. So it is taking energy to get this stuff to go into solution. And it's taking the energy from the water. Oh yeah, it's definitely endothermic. All right. I think that's everything in solution now. Then we just pour it back into the 50. And then top it up to 50 mils with water. Yeah. So there is my first solution. So hopefully that is fairly close to 0.1 molar sodium acetate. And then we just continuously rinse out our graduated cylinder with water. Hopefully you're near a sink, or I just brought a large bowl downstairs to. So now I've got my 0.1 molar acetic acid, labeled a cup, 0.1 molar acetic acid, and I want 50 mils of that as well. Oh, 50 mils. Yeah, if you take a sniff of the 0.1 molar acetic acid, you will notice it is not nearly as concentrated as the vinegar. Vinegar is a much stronger smell. About an 8-fold lower concentration than vinegar. Oh my, oh, right, my water. 100 mils of water. And again, you want to be using filtered water for this. You don't want to be using tap water. Some of the ions in tap water are going to interfere. I think most of the ions, most of the metal ions in tap water are not going to precipitate in the presence of acetate ion. Acetate ion is pretty soluble, but you never know. There's my 50. And 100. There we go. So we want 20 drops. 20 drops of the universal indicator in the water, and then 10 in the acetate and 10 in the acetic acid. I believe that is the, let me double check on that. Yeah. So you probably don't want to get this on your skin either. Just don't think it's particularly dangerous. It just will stain you. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 20. See, the water sort of takes this sort of yellow kind of color. And then 1, 2, 3, 6, 7, 8, 9, 10. Cool. Get a nice pink color for the acid. Let's see what color the conjugate base is going to be. 1, 2. Ooh, and a pretty blue, sort of turquoise color, or aqua. All right, so this will actually help us keep these three straight, since we sort of know what the different colors are. Let's see if I can find my color chart. Oh, here it is. So based on the color chart, you can see that neutral gives you, like around pH 7, sort of gives you a green color. I don't know, I guess you could call that green, kind of. Depending on the background, it kind of looks either yellow or, I guess that is green actually. And we know that acetic acid, at least 1 molar acetic acid, is a pH of around 3. So I would assume that 0.1 molar acetic acid has a pH of around 4, because it's 10 times less concentrated. So it would be 10 times less H plus ions. So it should be around pH 4. pH 4 is pink and pink. Makes sense. And then our acetate looks to be around pH 8. So pH 8 is right here. pH 9 is a purple color, so I don't think it's definitely, doesn't appear to be purple. Let's say it's more of a blue, and that looks more blue to me than purple. So I would give that a good pH 8. So now we want to make our 3 pH buffers based on different ratios of my acetic acid and my acetate. Hopefully you've done your calculations, because we did them already. Going to use my 10 ml graduated cylinder for this. I'm going to run out of water super soon. So pH 5.7. So pH 5.7 is more basic than the other two. So we're going to need more base. pH 4.7, we need equal amounts. And for the more acidic, pH 3.7, we need more acid. So I'm just going to add the right amount of acid to each one, and then the right amount of base to each one. So that's my most acidic. It gets the most acid. put on my transfer. Oh, here it is. Okay. Rinse it out with water and then add my base. Okay. Okay. Let me just swirl these up. Yeah, so what's interesting is that the pH 5.7 color now doesn't look like either one. It doesn't look like the acetic acid. The acetic acid is pink. The acetate is blue. And the 5.7 buffer looks more like the water, sort of like a yellowy color. Actually, because pH 6 is yellow. So that's the pH it should be. So your pH 5.7 buffer should be looking like pH 6. It should be yellow. 4.7 should be like a light sort of peach. It's pretty much what it looks like. And the 3.7 should be a little more pink. It's a subtle difference between the 3.7 and the 4.7, but you can definitely see it. All right. So I'm just going to take a transfer pipette and just put them one in each. That way I'll only use this transfer pipette for this particular buffer. And I'll get my plate ready. Make sure it's clean. Yep. You can just go right ahead and write on the plate if you want. I'm just going to put a T for top here so I'll know what the orientation, and B for bottom. Actually, T for top is good enough. So acetic acid in the first. Arrange these. So acetic acid in the first, water in the second, acetate in the third, one, two, three, and then 3.7, 4.7, 5.7. Okay. And we want 1 mil for each. Okay. So it's a good idea just to sort of lay them out in a column like this in the same order. That way you don't get lost, because I get lost with this sort of stuff all the time. So remember, the 1 mil mark is just below the bulb. It's right there. You could even take your marker and mark it to make it a little easier to see. It's probably not a bad idea. In fact, I'm going to do that. This would be much easier if we had a 1 mil pipette, but what are you going to do? Okay. So the first one, acetic acid. One. Two. Three. Four. And my water. One. Two. Three. Four. Gotta say, I'm impressed with how pretty these colors are. I didn't think it would be this obvious what the differences in pH are. And we can add another drop or two to the wells just in case the color doesn't really come through.
And you'll want a clean piece of white paper to put your plate on to take the picture. Because you're definitely going to need a white background to pick up the subtle differences in color. Because that difference between pH 4 and pH 5 is pretty subtle. Or 5 and 6, I mean. Oops. Oh, this one doesn't work. Okay. So I'm going to get a nice clean sheet of paper, put the plate on top. Move some stuff out of the way to get rid of some of these shadows. Try and get a decent picture. Yeah, lighting here kind of stinks, so I'm getting lots and lots of reflections and refractions. So I'll try one with the flash, see if that makes it better or worse. Yeah, I wouldn't recommend the flash. It didn't really work so great. What would be best if we had a light table? But of course, we don't have a light table. Yeah, if we could somehow light this from below, I think that would be the best. That's going to be tricky. Yeah, light table would just be perfect. So if you've got a lamp or something like that, I don't know, something like a flashlight or something, if you could put it underneath, that might be best. So now that I've got my picture, So the first column, we don't add anything. Second column, I'm going to actually probably write this right on the paper would be helpful. One drop of HCl. Third column, 1 drop NaOH. Fourth column, 10 drops NaOH. Yeah, so I would just recommend just writing that right on the paper. Right above the column that you're going to be putting it in.
Professor?
Yeah.
Do you still want us to add 1 drop of the indicator to each well?
You can if you want. Yeah, I think that was more of a thing for the second part, but yeah, feel free. Yeah, in fact, why don't we? It'll make it'll get, oh yeah, definitely brightens up the colors big time. Yeah, good suggestion. That was an excellent suggestion. Yeah, because now, yeah, the colors are much more intense than they were. Oh yeah, perfect, great idea. First prize. Who was that? Eva? Yep, I figured, yeah. Yeah, that looks so much better. That was an excellent suggestion. Just give it a little shake. Yeah, I'm gonna take another picture. Yeah, this is much, much better. Oh, no, I don't want the flash. All right. So I want to make sure I have the right acid in the right base. I want 0.1 molar rather than 1 molar. So if you have the 1 molar, make sure you dilute it by a factor of 10. All right, here we go. 1, 1, 1, 1, 1, 1. Now my hydroxide. One, oop. 1, 1, 1. Then 10 drops. 1, 2, 6, 7, 8, 9, 10. 4, 5, 6, 7, 8, 9, 10. 10. 10. 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4. 7, 8, 9, 10. Oh, yes, you see some dramatic differences. The high pH is a really pretty purple color. Oh. Oh man, pretty. All right. Time for my second picture. So yeah, it's kind of hard to show this on the screen because I don't want to tip it over. You can see that some of these look dramatically different than they did before. We didn't have that bright purple color that indicates a very high pH, 10 or above. We do not see it with acetic acid, however, because acetic acid is buffering sodium hydroxide. Yeah, it's almost too pretty to dump out, but dump out I must. And then just use some water to I'm gonna have to go get some more water. So how's it going so far? Everyone seen the pretty colors? All right, I just need to run and get some more water. I will be right back. Got more water. So the second part is everyone still working on the first part? Part one? You quiet people. DJ Ricky, you still working on the first part?
Just entering in the values now.
Oh, you can always do that later, you know. I always like do my analysis afterwards when I have plenty of time. With a cup of coffee or something. All right, so the second part is doing dilutions. So we want to make more of the 4.7 buffer, which is just equal parts acetate and acetic acid. Then we'll be using these 3 little cups for our dilutions. So I should label these dilution 1, dilution 2, dilution 3. Dill 1, dill 2, dill 3. There we go. Make more of the 4.7. So equal parts acetic acid and acetate. So my 4.7 buffer goes in the first row. First dilution goes in the second row, second dilution in the third, third dilution in the fourth. And each time I dilute them by 4 times, it looks like. Yeah. My dilution 1 is 1 to 4. 2 is 1 to 16. And 3 is 1 to 64. So quite dilute indeed. And it's 2 mils each time this time rather than 1. So it's going to take a while. All right. So you can take 15 mils of water and add them to each one of your 3 dilutions. So I'm just going to go ahead and do that. And you can use the water that has the indicator already in it. So I think we're going to stick with Eva's plan and add another drop to each one and get much better results. Okay. So I've got 15 mils of water in each of my 3 dilutions here. 1, 2, 3. So I'm going to put 5 of my pH 4.7 in the first one. And that'll be my first 1 to 4 dilution. I just love the colors. And you can see as soon as I added the 4.7 buffer to it, it turned from yellow right back to pink again. So I just swirl out a little bit, make sure it's nice and mixed. And then I'm going to take 5 of this and put it in dilution number 2. So we're doing what's called a serial dilution. Instead of using the same stock solution to make a bunch of dilutions, okay. So now this is my dilute solution. I want to dilute this one further. So I'm going to take 5 of this. There we go. And add it to dilution number 2, which again turns pink. Which it should. Even though this is dilute, it's still approximately the same pH. So our color should be the same. So I'm just diluting it with water And water isn't really going to change the pH terribly. Because remember, the pH of these solutions is based on the relative concentration of the acid and the conjugate base. And when I dilute them, that ratio doesn't change. They both get more dilute by the exact same. So the pH really should stay pretty much the same. So I mix this one up. Take 5 out of here. And add it to my third dilution, which turns pink again. So yeah, same color, which is what we would expect. These are all the same pH, but they're going to have radically different buffering capacities. Because this one, this third dilution, has 64 times less acetate ion and acetic acid than the original 4.7 pH 4.7 buffer. So this should get overwhelmed at a much lower concentration of sodium hydroxide than the others. At least that's what I'm thinking. So now 2 mils of dilution 1 in the second row, 2 mils of dilution 2 in the third, 2 mils of dilution 3 in the fourth. Oh, right, that's my one that doesn't work. And I guess we could just use the 10 mil. That might be a little faster. I'm going to see if that's any faster. Not really. I think if you use the graduated cylinder to add the 2 mils, there's more chance of spillage. So I'm not going to do that. I'm going to stick with my transfer pipette. Right, so that's my first dilution. Now I'm going to do my second one. Okay. Second dilution. Well, the third one. Okay, that took a while, but then when I put my white paper underneath it, they all look the same. Oh, and going to add another drop based on Eva's sage advice. Yes, we get a much brighter color with another dab in there. Swirl it around a bit. And we get that nice bright peach color, which tells you that is pH 5. There's no doubt about that. Right. Okay, my picture. Yeah, so I would recommend writing right on the paper. So for my dilutions, I want to have 1 drop of the 0.1 sodium hydroxide in the first row, 2 in the second, or 2 in the third, 3 in the fourth, 4th in the 5th. Just to be sure, just write it right on top. That way I will not forget. The more things you can do to idiot-proof a lab, the better. And believe me, I've idiot-proofed many in my day. So here we go. Make sure I have the right one. Yep, sodium hydroxide. 1, 1, 1, 1. And what you'll notice is that it does change color. but not all the way through. You'll have to do some mixing. Just like with the titration last week, when you got a drop of sodium hydroxide in there, remember the solution turned pink in a small part of the beaker or a small part of the flask, and then you swirled it and the color went away. Same sort of thing is happening here. All right, now I do my 2. 1, 2, 1, 2, 1, 2, 1, 2. And a pattern is beginning to emerge. 1, 2, 3. 1, 2, 3. 1, 2, 3. 2, 3. 1, 2, 3, 4. 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Oop. Let me do that one over. That's my dilution number 3. Here we go. One, 2. Now, the problem with trying to stir these with something is that you're going to contaminate them because there's wildly different pHs in each one of these. And unfortunately, they don't mix particularly fast. So I would mix them for like a good couple minutes. Oh, to have a plate shaker again. You don't want to shake it so hard that they spill over. So this has to be done kind of delicately. That looks pretty good. Okay. So you should see that the most dilute buffer really was only barely able to keep the pH relatively the same. The minute we added more than one drop, it just completely, the pH completely went to 10. Take the picture. There we go. All right, I'm going to move back.
So with your results here, use the color chart and try and determine the approximate pH plus or minus 1 for each of these. And then in the report template, there's some questions to answer. So I'll put that up there. So remember, you always put a title on your data table. And instead of like writing what the color is, here we want pH. Same with data table 2. And data table 2 goes on and on and on and on and on. And then so here are the questions. So the pKa of acetic acid is 4.7. What's the buffering range? So the buffering range is different from buffering capacity. Buffering capacity says how much acid, strong acid or strong base can I add, and the pH won't change drastically. The buffering range is where is it, what pH is it a useful buffer? And remember, the best buffer has relatively equal concentrations of acid and conjugate base. So there you go. So then just a couple of calculations, dilutions. We've basically done these before. We've actually done this particular calculation already, number 6. Number 7, pretty much the only thing you may have trouble with are questions 8 and 9. So like I said, I will go through this and probably post another video on ice tables, because that was something we didn't really do. Actually, I'm kind of surprised the questions here, to be honest. But I mean, it gives us an opportunity to learn. So yeah, we didn't do ice table. It's in class. So what I will do is have just like I did with the pKa calculation, I will make a separate video on ice tables and take you through this calculation. And then you should be able to answer question 9 as well. So any questions about either the report or how to answer the questions or anything else before we wrap things up?
Professor?
Yep.
It says here initial color. Do you still want us to place the color? Because below it is the initial pH. So it's going to be both numbers for
Oh, for which, for
the table 1?
Wow, does it actually say that? It does, doesn't it? Oh, yeah. Yeah, that's only the first one. Yeah, so the initial color there, yeah, you could put in whatever you think that color is, and then the pH that it corresponds to. I think it's peach, but you may think it's some sort of other exotic color. You may say, no, 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 professor, you're an idiot. It's quince. It's like, fine, you win.
Okay, thank you, Professor.
Mm. Or, it's Caucasian, however you want to describe that particular color.
I would still go with peach. It looks like peach.
Probably. That's probably wise.
Professor, I have a question.
Mhm.
Is the lab report template already on Canvas? Because I don't see it.
Oh, maybe I haven't released it yet. That's a really good point.
Okay.
I'll do that right now.
Okay, thank
Thanks,
you.
Leah. Yeah, I'm constantly forgetting things. Oh. Oh, right, and I need to post it in Word form. I will do that. All right, I just posted the PDF and I will put the Word document in there right now. Oh, oops. All right, they're both there now. So both the PDF and the Word doc are there. So yeah, thanks for pointing that out, Leah.
You're welcome. Thank you.
Right, any other questions before we, how you doing, Chris? You almost done? Sweet. Maria's got her headphones on. Are you listening to us on Bluetooth or something, Maria?
No, I'm listening to the class.
Well, that's what I
Yeah.
said. Yeah, have you got us on Bluetooth there?
Just from family difference here. Yeah.
Oh, is there a lot of noise where you are?
Yeah, kind of. Yeah.
Yeah, well,
Yeah. That's why.
yeah, that's why I don't do the lab upstairs. Like the dogs would make way too much noise. Right, anybody else? Brittany, Kim, Renee, Ricky, Alyssa? You all good? I didn't see much of you guys this week.
All good on my
Doing
end.
good.
Oh, yeah, Rick, your camera's
Yeah,
still
my
messed up,
stupid
is it?
webcam this does not work for Zoom. I don't know why.
So you can make video calls, but not,
Well,
is it a tablet?
FaceTime I can't either. So I can't do video calls on anything.
Is it a tablet or a,
On my phone and my laptop.
no, that's wow.
And my tablet doesn't work. I had an iPad, but then that doesn't work. So I only have a phone and a computer.
Good old technology. It never fails us. But do you have any questions, Alyssa, about the lab? So you're able to see us, but you can't.
Yeah, I'm able to see you. Yeah, and
Okay.
I can hear you. I can hear you perfectly fine.
Okay.
Yep, no questions as
All
of right
right.
now.
Sweet. All right,
Thank you.
so I'm probably gonna wrap it up then if there's no other questions. Yeah, all this stuff, just like the usual, can just go down the sink. Because basically it's fairly neutral pH. We've neutralized most of the strong acid and strong base. So there's nothing, it's just acetate, nothing particularly harmful there. Man, though, it did make a big mess though, didn't it? I'm kind of impressed with how much of a mess it made. And I made it at my wife's office, so she's going to be thrilled. So I'll have to clean it up before she goes to work tomorrow. All right, everybody. Thanks for hanging.
Thank you, Professor.
Thank
I'll
you.
talk to you
Bye,
soon. Have a
Professor.
Thank you,
great
Professor.
weekend.
You too.
We'll see you soon.